Now we have the next characterization algorithm, which is UPGMA. And please take a look at this website. It has a very nice animation. It tells how to you construct a hierarchical clustering result step by step. And we have another slide. So the content of this slide is from that website. Okay. So this algorithm is called UPGMA, unweighted paragraph group method with arithmetic mean. So let's take a look at the result of the this algorithm. Okay, so sometimes when we want to analyze the relationship between different data points, we will use a tree. So here is the result of this algorithm. Okay, at the right hand side. Okay, we have several different data points right here, and as you can see, we can use a tree to demonstrate what is the distance between different data points. For example, right here, that means the data point F and data point B, they are closer than the other data point. So the height right here is the distance between two data points. So take this one for example, B and F. So the height is 0.5. So that means the distance between B and F is 1. So you can group B and F right here. And then these two data points, okay? We further group B and F with G. That is because among these, the rest of the data points, okay, G is close to data point B and F, and height is right here. The distance is right here, okay, is 6.25. Okay, so and we can further do such kind of grouping step by step to group all the rest of the data point, and until right here we grouped all of the data points together by using a tree-like structure. So I will show you how to construct this tree by using this example. Okay, so in the first place, we have to calculate the distance matrix. Okay, so that is the distance matrix of those data. Okay, so right here again, as we mentioned, distance of A to A, that means the distance between one data point to itself is 0. Okay, it should be 0. So the diagonal values on in this matrix, the diagonal line should be 0, and 19 is value. That means the distance between A and B, and so on and so forth. And as we mentioned, it is a symmetric matrix. So right here it should be 19 as well. But usually we only need the value right here. Okay, so you have to prepare a distance matrix before you apply UPGMA. Okay, so again, the first step of UPGMA is to find the smallest distance in this distance matrix, and that is B and F. So that means you should group B and F at the very first step. Okay, the distance between B and F is 1. Okay, but when you draw the UBGMA tree, okay, the height right here should be 0.5 because the distance between B and F should be 0.5 plus 0.5 and equals 1. Okay, so that is the first step. Okay, and after you select the smallest distance, okay, you delete this column and this row. Okay, because you remove the data point B and data point F, but you group these two data points, so you have to create another new data point, which is BF. Okay, so the next step is looks like this. You add another new data point, which is BF. It represents the cluster of B and F. And you have to update the distance matrix. So right here, and of course the rest of the distance matrix is exactly the same as the original one, but you have to calculate the distance of between point A and BF, this value. Okay, since the algorithm is the math with arithmetic mean, that means you have to calculate the mean value of the distance. So the distance of between BF and A is exactly the average distance of A and F and B and F. So you can find this value from the original distance matrix, which is 19 and 18. So the average number should be 18.5, right? And right here, the distance between BF and C should be the distance of BC and FC. So you can find this value right here and here, and so on and so forth. So you can easily update the new distance matrix by using the old distance matrix. Okay, so you calculate the mean pairwise distance. Okay, so we have the new distance right here, and as you can see, we again choose the smallest one, which is A and D, right? So we draw A and D and we group them together, okay? And the height of the tree is 4, because 4 plus 4 equals 8, which is the distance right here. And again, we remove A and D, okay? And we create a new column and row represent the cluster of A and D. And we further update the new distance matrix. Okay, and again, right here, okay, the distance of between AD and BF is exactly the distance, the average distance of AB, AD, DB, and DF, which you can find in the original distance matrix, which is right here. So simply just average them and put the answer right here. And again, update the distance of AD and C, which is, you can find a distance of AC and AD in the original matrix and average them, and so on and so forth. So next step, again, find the smallest value in this matrix, which is this one. So that means you have to group G and BF, which is right here, and the height of the tree is half of 12.5, which is 6.25. and so on and so forth. And again, remove this column and row. Create a new column. Create a new column right here, and so on and so forth, so on and so forth. So you can eventually create this tree by updating the new distance matrix. Okay, at the end, you can merge every node. Okay, and you can calculate this value. So that's how hierarchical clustering works. Okay, by updating the distance matrix. Okay, so because it is very straightforward and the result is very easy for you to understand. So hierarchical clustering is very useful when you do clustering. Okay. That is another example. Sometimes we use hierarchical clustering to represent different species, right? That is so you can see that it can cluster different species in a very nice way. And after you perform UPGMA, okay, you have to you can set a threshold. Okay, for example, we set a threshold at 825, and you can see that this part is a cluster, and we have two data point which is not belong to the cluster because they are grouping at the point which is higher than 825. So that's how you do clustering. Okay, you can set the threshold, but for the hierarchical clustering algorithm, user have to the user have to decide two different things. The one is the distance function you select, and the second thing is the threshold you select. Okay, so that is the website. Please take some time to take a look at the website. Okay. Usually we don't write Python program to draw the tree because it is not that the tree. First, you have to provide the distance matrix, and you only need 3 or 4 line of code to generate the tree. But that is not that beautiful, right? So sometimes we use orange to draw the tree. Okay, you can draw it in this way or this way, which is okay. And of course, as we mentioned, you can select the distance function by yourself. So here we provide another example, which is that distance matrix is from the categorical data. So that means we have 4 points, 1, 2, 3, 4, and we have 5 different features, and they are all not only categorical data, they are binary data. But it really doesn't matter because we can calculate the distance matrix by using the value you provide. Okay, so after we have the distance matrix, we simply just draw a result. Okay, so that is the result, and we can, for example, we can set the threshold right here. So we know that data point 1 and 3 is much closer 2 and 0 are closer than are closer, but this data can be clustered into 2 different clusters. Okay, so that's how we use it. And the next clustering algorithm we talk about is dbScan. Okay, dbScan. We will not explain how dbScan works because it is a little bit complex. We need some animation to help us to understand what is dbScan. So please now stop this video to take a look at this one, the blue links. Okay, it is a short video too. It has an animation to tell you how to run dbScan by an example. So please take a look right now. Okay, stop this one. Okay. So I guess you watch the video right here. So let's take a look how we handle dbScan in Python. Okay, and again, sklearn has the dbScan library. So you simply just right here. You simply just use a very simple line code to run dbScan, and as you can see in the video, you have to tell dbScan what is the epsilon of your setting. Okay, what is the minimal samples in the small circle or in the small area. So dbScan can output the result like this. So as you can see, we have 3 different clusters in this example, and right here, those are data points which it cannot be clustered into the 3 clusters. And as you can see, we can and as we can see that there should be some. Take a look at this one. The big circle right here, they are core point, and the small point is non-core point. Okay, and the black point is the noise or outlier that cannot be clustered into the 3 cluster. So let's compare the difference between k-means and dbScan. And as you can see that for some data point which is a little bit far away from the core point and non-core point, they cannot be clustered. Okay, but for k-means, okay, in the same data, when we set the number to k equals 3, okay, every data point in the k-means, they should belong to some cluster. There's no outlier or any noise in k-means because they are enforced to be classified into some cluster. So there should be 3 central E right here. Okay, and every point will be clustered based on the distance between the data point and the other central E's. Okay, but for dbScan, okay, it's really depend on how you to decide what is the for example, what is the small circle to determine which point is the core point and which point is the non-core point. If you set the radius a little bit bigger, and this point might become non-core point. Okay, this point become a core point, but it is a little bit dangerous if you set the radius bigger because of the data sample right here. if you set the circle, the radius a little bit bigger, it might consider to combine these two clusters into one big cluster. So from my experience, when I use DBScan, I will set the radius of the circle to be a small value, even if it breaks these clusters into even more small cluster. But for me, it is okay because I can later to combine different cluster into one cluster. Okay, and from my experience, I will set the k value of k mean to be larger, so that the result will not be affected by far away outliers. Okay. So I would like to introduce a data set, okay, which is malware cause. Okay, you can download it from this website, this GitHub, and I would like to show you the result. It is a zip file, and when you unzip the file, you can see that there are several directories right here, and each directory is the sample of some malwares, and that is the name of the malware family. Okay, we have several malware family. Okay, each subdirectory represents one malware family, and in each directory, okay, we have a lot of samples in each malware family. Okay, so let's take a look at one of the examples. So that means that is the low money malware, and we have a sample, and we collect the Windows API call of that malware when it was being executed. So here is the example. It is a very oversimplified example, but we think it is okay for teaching. Okay, so the first Windows API call invoked by this malware is the library. Of course, when you execute Windows API call, there should be some parameter, but we remove the parameters for simplicity. Okay, so the first call is load library, and we have registry query value and some other Windows library. So it is a call sequence. So here again, that is the this malware, and that is the number of Windows API call called by the malware. Okay, 42 times calling load library, 340 times calls registry query value, and so on and so forth. And as you can see, which here is an example of low money family and hot bar family, and you can see that the call pattern of these two family looks different, right? Looks different. So we want to see if the call distance can help us to distinguish different malware samples. So we construct a table. Okay, so that is a name and a family of malware samples, and we calculate. Okay, we count. There will be several Windows API calls being called, okay, in this data set, and we put the number of calls, okay, by this malware. Okay, so this malware called 36 times of load library, 82 times of create file, and so on and so forth. And as you can see, there's some NaN, which means non not a number value right here. That means this sample did not call create thread. Okay, so we simply use this table. We want to use this table as our data set. Okay, so again, we fill the not a number, okay, to 0 by using this value, or by using this line of code. And we would like to create another different table, okay, which is, if this value is non-zero, we put 1 right here, 1, 1. If it is 0, we put 0 right here. Okay, so malware binary code data table, that means if that we record if the malware call this library, yes or no. So it is a binary table. And the malware code table store the number of calls, okay, in that table. So we have two different tables. One is the actual number of calls, and the other is the binary number. Okay, so we can use the clustering algorithm we teach you today to analyze the table. So first one we use is the UPGMA. So we calculate UPGMA. We calculate the distance matrix here and draw the result. Okay, and right here, that is the distance matrix. Okay, so we use the call data table, okay, and draw this value. And as you can see that it seems like the result of UPGMA looks good. So you take a look at this part, and you can see that okay, low money, and the GRAFTOR. Okay, although you can see that two family are grouped together, but it indicates that a low money and the G family right here, they have similar call pattern in the table, right? And you can see that the purple one, the pink one, okay, you can see that all the samples of SYTRO family, they are grouped together because they have similar call patterns in that table, and so on and so forth, so on and so forth. And so that you can use the cluster algorithm to do such kind of analysis. And even though you can take a look at this one. Okay, that is cryptic. Okay, and cryptic. So that after we have this tree result, we know that cryptic has two different behavior when using Windows API call. So they are not in the same cluster. Okay, so that you can do such kind of analysis on Windows malware. And something like here, that means the LORING family, although they are in this, they are labeled as the same as the sample of same family, but actually their call pattern are not that similar, right? And that is how we use UPGMA to analyze malware calls, and that is the result. That is the UPGMA value we use binary call as our input data. Okay, so that is similar, and also we can use k-means to analyze the malware. So k-means will output the cluster number of your data. So as we can see that the hotbar samples are clustered to cluster number 8, and the cryptic samples are clustered into cluster number 6. Okay, and before we finish, we'd like to show you something by using orange. Okay, so so okay, so let's take a look at the orange. Okay, so we can simply just use the iris dataset. Okay, we have 4 features and 1 categorical data, right? So for clustering, we can, for example, using hierarchical clustering, right? So here's a group of widget which is unsupervised learning. So before we perform hierarchical clustering, we need to calculate the distance, right? So we connect the data to here. So here's the distance matrix. It will be output to the hierarchical clustering. It is very simple to use orange to draw the hierarchical clustering. And in the distance widget, you can select any distance you learned: normalized, Euclidean distance, Manhattan distance, or Jakarta distance, or cosine similarity distance, cosine distance. Okay, so we select Euclidean distance right here, and we connect it to the hierarchical cluster. And you can see that the average right here, that means UPGMA. So you can see that we have several different flowers right here, and you can see right here most of the Virginica is clustered in the cluster right here. You can click, you can adjust your threshold right here. So you can see that in this cluster number 11, all the samples in this cluster is iris Virginica. Again, you can adjust the threshold to here, and you can see that most of the Virginica fell into cluster number 7, but one versicolor is clustered into this cluster. But it really doesn't matter because it relies on the distance function. Okay, so you can see that versicolor and Virginica is mixed in this cluster, but you can slightly tweak the threshold, and you can see that okay, 4 of the versicolor it will be clustered into cluster numbers 10, and so that it makes the cluster a little bit meaningful. Okay, so you can tweak it, but and of course you will not set a very low cluster threshold in UPGMA. Okay, so that is cluster, and also you can use dbScan, okay, to simply just output the result of dbScan. Okay, so again here the color right here, it specify if the data point is a core point or a non-core point right here, or a non-core point. So it will generate the cluster number in right here. Okay, so you can do so. Okay, so after that you can use you can draw the figure. So you have to use for example, we use a scatter plot right here and right here. Okay, from data to data, and we can plot them Okay, so the color right here is the original label, which is iris, but you can use a shape data right here to specify if it is a core point or it is a non-core point. Okay, or you can use the shape to identify the clusters output by the DB scan. So it is quite easy for you to understand the result of the cluster. Okay, and of course you can um, use the result of hierarchical clustering to demonstrate. Okay, so so as you can see that you can compare the clustering result of UBGMA and so that you can see that for UBGMA, because we have a very low threshold, okay, we can adjust the threshold to somewhere, for example, right, I think right here it is okay. Okay, so you can compare the result of UBGMA and DB-scan by visually. Okay, visually. So that is the clustering, and of course we have k-means. So in the unsupervised, we have k-means right here. Okay. Oops. Okay, there. I think. Sorry, there's something wrong with it. Okay, when you apply k-means, it will show you the some score which is very similar to the elbow, and you can see that you can use this figure right here to determine what is the what is the k value you like to choose right here. Okay, so there's something wrong with this widget. Okay, but let's see if it works. Okay, no, it's not working. Maybe that is because let's do it again. Okay, okay, there's something wrong with it. See if we can fix it by selecting only x value. Okay, that means we remove this one. We no. Okay. That means the data. Okay. Let's try this one. Okay, we will think. Okay, there may be something wrong with this data set. Okay, let's see. We'll see it later. Okay, so that is how we use Orange to apply clustering algorithm. Okay, so we stop right here, and we'll continue next hour. Okay.